Welcome. I'm Dr. Eugene Torgoy. I'm a college professor with a PhD in physics. I've taught math at the college level for many years. I've used that experience to create this series of videos to help you master completing the square. I've broken this topic down into easily digestible steps that will allow you to master this topic. Although there are 9 parts, this series can be grouped into 4 distinct sections. The first section establishes the conceptual foundation for completing the square. The second section will teach you how to complete the square for the basic problem type. The third section will teach you how to complete the square for advanced problem types. And the fourth and final section will show you examples of how you might use completing the square in future courses. Let's begin by discussing the quadratic function. The quadratic function is f of x equals ax squared plus bx plus c, where a, b, and c are numbers. This function has 3 terms. The first term is called the quadratic term. The second term is called the linear term. And the last term is called the constant term. The number multiplied by x squared in the quadratic term is known as the quadratic coefficient, or sometimes the leading coefficient. The number multiplied by x in the linear term is called the linear coefficient. We'll use these names throughout this series. Completing the square is a technique typically taught in an algebra or pre-calculus course. It is usually used to find the roots of a quadratic function. When a quadratic function is set equal to 0, the values of x that satisfy this equation are called the roots of the equation. These are also known as the x-intercepts. The graph on the left shows a quadratic function y equals negative x squared minus 5x plus 10. The x-intercepts are the values of x when the curve crosses the x-axis. Next, let's talk about the conceptual models for completing the square. Conceptual models are very important and form the basis of one's understanding. These models are ways of thinking about the process of completing the square. Without these kinds of models, some students find that while they can perform the process, they don't understand what they are actually doing. Let's begin with a numeric model. Numbers are often useful to make ideas more concrete. 25 is a perfect square because it can be written as 5 squared. If we have 12, written in an equation, 12 equals 12, what would we need to add to write this number as a perfect square? We add 13 to both sides to keep the equation balanced, but only evaluate it on the left-hand side. We get 25 equals 12 plus 13. 25 can then be written as 5 squared, so adding 13 allowed us to write the left-hand side as a perfect square. For the puzzle model, imagine a puzzle missing one of its pieces. By looking at the whole, could you determine the shape that would complete the square? There is a geometric interpretation of completing the square, where the process is literally determining how much area you would need to add in order to draw the shape as a square. For the cloud model, imagine looking at a cloud. What could we add to this cloud to make it match a recognizable pattern? If I add legs, horns, and a head, you can see it is now easily recognizable as a ram. Hopefully you can see what all these models have in common. In all of them, we add something to them so that we can make them match a particular pattern. Unusual and fun models are often easier to remember, so when you're developing models on your own, try to be as creative as possible. Finally, here's the transformer model. If you're not familiar, a transformer can transform from a robot into a car and back. Imagine that a transformer is on a scale and is in balance with an equal weight box. Unfortunately, this transformer is missing an arm and can't transform. What do we need to add to this transformer to allow it to change into a car? An arm. But we need to add arms to both sides of the scale to keep the scale balanced. Now that the transformer is complete, it can transform into a car. This process is analogous to completing the square for a quadratic equation. In that case, we figure out what we need to add to the equation so that we can rewrite it in a more compact form. That concludes this lesson. If you liked it, then click the like and subscribe buttons below. In the next video, we'll discuss how to square a binomial expression using FOIL, and also introduce the perfect square pattern, and use specific cases to verify the pattern. See you then.